Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Transceivers are a key element of modern network design, serving as the bridge between networking equipment and the cabling infrastructure, particularly in high-speed and fiber-based environments. These compact modular devices convert electrical signals generated by switches, routers, or firewalls into optical or electrical signals that can travel over different media types. Transceivers are installed directly into device ports, allowing network administrators to customize port functionality for the required cable type, distance, and speed. Rather than purchasing different switches for different interfaces, you can use a standard switch with open transceiver slots and insert the appropriate modules to match your needs. The Network Plus exam emphasizes transceivers because they are widely used in enterprise environments and appear in multiple objective areas. You will encounter transceiver questions when studying media types, port-based device configuration, or network hardware. These questions may ask you to identify a module type based on appearance or scenario, determine the correct transceiver for a given fiber mode and distance, or understand how to match a module to the device slot. With the increasing reliance on fiber connectivity and modular switch design, transceiver literacy is essential for both the exam and hands-on network work. A transceiver module is a self-contained device that combines a transmitter and a receiver into one unit. The transmitter converts electrical signals from the switch or router into optical signals, while the receiver does the opposite, converting incoming optical signals back into electrical signals that the device can understand. These modules are inserted into specially designed slots on network equipment, commonly called small form factor pluggable SFP ports. By using pluggable transceivers, organizations gain flexibility in how they deploy switches and routers, allowing a single piece of equipment to support multiple cable types and speeds with simple module swaps. The most common transceiver type in enterprise networks is the SFP, or small form factor pluggable module. These modules support data rates of 1 gigabit per second and are compatible with both single-mode and multi-mode fiber depending on the specific model. SFPs use LC connectors for fiber termination, and they are widely supported across networking gear from many vendors. They are hot swappable, meaning they can be installed or removed while the switch remains powered on. This allows for rapid deployment, maintenance, or reconfiguration without downtime. SFP Plus modules are an enhanced version of the basic SFP and support higher data rates, typically up to 10 gigabits per second. They share the same physical dimensions as SFP modules and are often backward compatible in devices that support both SFP and SFP Plus. .SFP Plus modules are commonly used in uplink ports on access layer switches or for aggregation connections in distribution switches. While they use the same LC fiber connectors as SFP, they require higher quality fiber and transceivers to maintain performance at the increased speed. For even higher performance, particularly in data center and backbone environments, QSFP and QSFP Plus transceivers are used. These quad small form factor pluggable modules support 4 simultaneous data channels allowing speeds of 40 gigabits per second or more. QSFP modules are often used for high-speed uplinks between core switches or in leaf-spine architectures where low latency and high throughput are priorities. QSFP modules can be used with MPO or MTP connectors, which handle multiple fiber strands within a single connector, simplifying dense fiber installations. Bidirectional, or BIDI transceivers, offer a solution for organizations looking to maximize fiber utilization. BIDI modules transmit and receive data over a single strand of fiber by using different wavelengths for each direction. This technology allows existing single-strand fiber runs to support full duplex communication, effectively doubling capacity without installing new cable. BIDI modules are especially useful in facilities where adding fiber would be expensive or logistically challenging, such as retrofitted buildings or leased infrastructure. Wavelength multiplexing technologies, such as coarse wavelength division multiplexing and dense wavelength division multiplexing, DWDM, allow multiple signals to be transmitted simultaneously over a single fiber by using different light wavelengths for each channel. These technologies are supported by specialized transceiver modules designed to encode and decode signals using specific wavelengths. CWDM modules are often used in enterprise campus links, while DWDM is typically found in telecom and ISP infrastructure, supporting long-haul, high-capacity data transport. Not all transceivers are compatible with all network devices. Each transceiver must match the form factor of the slot it is being inserted into. Standards such as SFP, SFP+, QSFP, and QSFP28 define the physical and electrical specifications of these modules and are governed by multi-source agreements between manufacturers. These standards ensure that transceivers from different vendors can interoperate in compliant devices. However, not all equipment supports every module type, and some vendors implement firmware-level checks that may block unsupported or third-party modules from being used. Copper SFP modules provide another option for environments where fiber is not required. These modules convert an SFP port into a standard RJ45 Ethernet port, supporting copper cabling for gigabit Ethernet. Copper SFPs are useful in mixed media environments where most links are fiber, but some short-distance or legacy links use Cat5e or Cat6 twisted pair cabling. They are particularly helpful in wiring closets or branch offices where fiber runs may not be available or necessary. Inserting and removing transceivers is a straightforward process but must be done with care. Most modules use a latch or pull tab mechanism to lock into place. Inserting the module involves aligning it with the port and pressing gently until it clicks. Removal is typically toolless. Either a latch is depressed or a tab is pulled to disengage the locking mechanism. While hot swapping is supported in most devices, best practice includes verifying compatibility, checking device logs after installation, and ensuring that the module is inserted fully to avoid link errors. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. When deploying fiber-based links, one of the most important considerations is matching the transceiver to the appropriate fiber type and connector. Most SFP and SFP+ modules are designed to work with LC connectors, but they must also align with a specific mode of fiber, single mode or multi-mode. Single mode SFPs are designed for 9-micron core diameter fiber and work with laser light sources for long-distance transmission. Multi-mode SFPs, on the other hand, are optimized for 50 or 62.5 micron fiber and use LEDs or VCSLs. Installing the wrong transceiver for the fiber type will result in weak signals, high error rates, or complete loss of connectivity. In addition to mode compatibility, transceivers are labeled with distance ratings using industry-standard suffixes such as SR, LR, and ER. These suffixes help identify the intended range and fiber type. SR stands for short range and typically refers to multi-mode fiber with ranges up to 300 or 400 meters. LR stands for long range and is used with single-mode fiber, supporting distances up to 10 kilometers. ER, or extended range, can push the range to 40 kilometers or more depending on conditions. Understanding these suffixes is essential when selecting the right module for a given fiber path, especially in mixed environments or WAN links. As transceivers handle data at increasing speeds and over longer distances, they also generate more heat. Devices such as switches and routers are typically designed with heat dissipation in mind, but densely packed transceiver ports can still strain the thermal profile of a device. High-speed modules like 40G and 100G QSFP transceivers may require airflow management or specific slot placement to maintain optimal temperatures. If a transceiver overheats, it may automatically throttle performance, shut down the link, or trigger alarms in the device interface. Proper spacing, ventilation, and adherence to environmental operating conditions can help prevent thermal issues. Many modern transceivers include built-in diagnostic features under the banner of Digital Optical Monitoring, DOM. These features allow network administrators to monitor real-time optical parameters, such as transmit and receive power levels, temperature, voltage, and error counts. DOM data is accessible through the switch or router's management interface and can be used for proactive troubleshooting or capacity planning. For example, a declining receive power level might indicate a dirty connector, fiber damage, or an aging light source. Early detection allows for preemptive maintenance before a full-link failure occurs. Another challenge associated with transceivers is vendor lock-in. While the form factors may conform to open standards, some network hardware manufacturers use firmware restrictions to limit compatibility with third-party or generic modules. These restrictions may cause the device to reject the transceiver entirely, issue warning messages, or operate at reduced capacity. Certified transceivers from the original manufacturer are often more expensive, but they guarantee compatibility and support. Some administrators choose to use third-party modules to reduce costs, but this requires careful vetting and may impact warranty or service agreements. Inventory management for transceivers is important in medium to large network environments. Each module is typically labeled with its type, supported speed, distance rating, and vendor information. Proper labeling ensures that modules are installed in the correct locations and can be easily replaced when necessary. Maintaining an inventory database with serial numbers, locations, and usage status helps with capacity planning, troubleshooting, and replacement scheduling. Transceivers should also be stored carefully to prevent damage to the optical components. Even minor contamination or mechanical stress can impair performance or render a module unusable. Pluggable transceivers provide significant benefits for both network scalability and maintenance. They allow network engineers to customize port configurations without needing to purchase purpose-built hardware. For example, a single switch model may support SFP, SFP+, and copper modules in the same chassis, enabling a mix of media types and speeds as needed. This modular approach simplifies equipment purchasing, reduces rack space requirements, and extends the life cycle of core network devices. When speeds increase or network designs evolve, upgrading just the transceiver is often faster and cheaper than replacing entire switches or routers. In the Network Plus exam, transceiver knowledge is frequently tested in both visual identification and scenario-based formats. You may be shown a diagram of a switch with labeled ports and asked to choose the appropriate transceiver for a given application. Other questions may describe a need for a high-speed uplink and ask you to select between SFP+, QSFP, or copper option. You could also be presented with a troubleshooting case where a link is down and need to identify that a mismatched transceiver or incompatible fiber type is the root cause. These questions require familiarity not only with the names and speeds of transceivers, but also with how they are used in practice. Transceiver questions may also test your ability to recognize appropriate usage in network topologies. For instance, in a leaf-spine data center architecture, QSFP modules may be used to provide 40 G-links between spine and leaf switches, while SFP+ modules handle 10 G-links from leaf switches to servers. In a campus environment, SFP transceivers may be used for 1G fiber runs between wiring closets and the core. These real-world design principles are reflected in exam scenarios, making it important to understand not just the specifications, but also the deployment patterns associated with each transceiver type. In summary, transceiver modules are essential components that enable flexible and scalable network design. They allow networking devices to adapt to different media types, speeds, and applications without the need for entirely different hardware. Whether you're deploying SFPs for gigabit Ethernet, using BiD transceivers to maximize fiber utilization, or installing QSFP modules for high-speed backbone connections, selecting and managing transceivers correctly ensures reliable performance. Mastery of transceiver types, compatibility concerns, and practical applications is a must for the Network Plus exam and for effective real-world network engineering. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, Make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.